Thank you very much. I mean, I'm going to try to include some empirical stuff. So it's not going to be purely theoretical, I promise everyone. There will be something for everyone here. So I'm Jesse. So first of all, thank you to the organizers for inviting me. I'm very glad to be here and be talking to all of you. As you can already see, today we're going to be talking about singular learning theory for alignment. Now, developmental interpretability isn't up in that title, but we will get to that at the end. Yeah, so I'd like to start with an observation. And that observation is that deep neural networks work. Right? Over the last 10 years, 15 years almost, we've seen deep neural networks and technologies built on top of deep neural networks solve many, maybe most, long outstanding problems in computer vision, reinforcement learning, natural language processing. But the remaining questions are, there are still remaining problems, but the remaining problems are maybe problems that will be solved purely by scaling up current techniques with a few tinkering-like solutions on top of those. But it seems like those questions are questions mainly about degree rather than quality. Okay, there's a natural follow-up question, which is why? Right? What is it about neural networks that makes them so special? The answer I'd like to propose is that deep neural networks are special because they learn algorithms. Okay, so I'm thinking of work like that done by Wang et al. On the indirect object identification circuit. So people have uncovered these serial steps in which models learn to form principled representations of the data, transform those in principled steps to make predictions about what's coming next. Thinking about work by Neil and others on interpreting transformers trained on clear algorithmic tasks, where we can actually understand what the model is doing internally. And I'm thinking of earlier work, even in the context of vision models, where we see that vision models learn to hierarchically compose features in order to build up rich representations of the world. So in all these cases, neural networks learn to form good representations and to compute on top of those. I'm going to save questions for the end, because we've got a lot to go through. That makes neural networks qualitatively unlike earlier kinds of approaches to learning. Right? Take regression, Gaussian processes, clustering. None of these classical techniques is ever going to learn to sort a list, for example. Neural networks are different in that their hierarchical and flexible structure, internal structure, lets them internalize and reflect the rich computational structure out in the world. And this is a double-edged sword. Right? The same ability that makes neural networks so flexible and capable also makes them dangerous. That's especially true because many of the capabilities we most associate with catastrophic risk are fundamentally algorithmic. Abilities like planning, choosing a goal out in the world, thinking of steps to pursue to reach that goal. Abilities like error correction, making adjustments to your plans in response to a changing world. Abilities like the ability to model the beliefs and intentions of others, and then to manipulate those beliefs and intentions. Learning algorithms is currently more powerful, but less reliable than programming. We're in a kind of proto-alchemy state, in which we take some data, throw it into a cauldron, and mix it with our big witch-like ladles or whatever it is, and then hope to get something aligned out of that process. I think something better is possible. I think a mature field of alignment looks something closer to industrial chemical manufacturing, right? Incredibly difficult. Something that required decades to get right, maybe. Maybe we can accelerate that a little bit. But ultimately something precise, where we understand the building blocks involved and we understand how to design systems that produce what we want them to produce. So in my view, alignment, the technical problem of alignment, which I'll define in terms of intent alignment, or trying to reliably get AIs to be aligned with anything at all. Right? I'm going to put aside the social component of this question for today. I view alignment as being about learning how to reliably program neural networks. Now, programming is not automatically more reliable. Right? Plenty of examples where explicitly written code has gone horribly wrong in human history. That also means that any individual approach that gets us closer to alignment as programming probably is not enough. We need some suite of techniques involved, different standards, infrastructure, tools. Yeah, expecting, for example, evals to solve alignment is like expecting unit tests to solve computer bugs. If you've written a program, you know that this is not true. Test-driven development is an ideology. It does not solve programming. Expecting red teaming to solve alignment is like expecting red teaming to solve computer security. It doesn't, right? Things still get through the cracks. We need it. These are important components. These are the first things you're going to try, but they're not necessarily enough on its own. Maybe expecting SAEs to solve alignment is like expecting log files to solve infrastructure issues. Now, I think this is a little unfair to SAEs in that they're actually cooler than this. But the point stands that with log files, you only see what you're logging. And the main failure with an approach like SAEs might be that there are parts of your model that you don't catch, that you're not logging. If you then look at the log files and you don't account for the things you might be missing, you might miss very important parts of your infrastructure. Okay, so I think alignment requires better tools. We might be safe with the current techniques. I would like more techniques. I think of what Evan Hubinger has called understanding-based evals. So maybe in this analogy, that's things like memory profilers, interactive debuggers, linters, static analysis. Understanding-based evals, nobody really knows what they are yet, but we'd like to have some understanding-based evals that actually tell us about what's going on inside of models. And it's not just telling us about input-output behavior. Maybe alignment requires better design approaches, new ways to train models that are inherently safer. Right? What is the borrow checker of Rust for alignment? I don't know if that question makes sense. And maybe, just maybe, we need an IDE. Right? We need to be able to read the program that is the neural network. I want it to be well documented. I want clear code comments in the right places. I want names that make sense for the different functions it's calling, what's actually going on inside of the model. I think it helps. I'll come to that in a second. This is my main hope for what a mature science of deep learning could accomplish. Theory informs the construction and development of new tools. Because they're grounded in theory, we can extract more bits from those measurements. That's what theory allows us to do. We know that they're related to the things we actually care about, and those tools let us develop a more reliable programming of neural networks. Let's put this in context. So I really like this figure that Anthropic came up with last year, where they have this map of how difficult they think alignment is. And they have this distribution over difficulties, which is obviously very qualitative and vague. But anyway, so let's substitute in my own personal views onto this figure. Well, first of all, I think it's a little ambitious to call constitutional AI as on par with the difficulty of the steam engine. But maybe SAEs are, right? Or maybe the current stuff that people have done with scaling SAEs to Claude Sonnet is on par with the steam engine. Now, my own personal distribution of risk is a little more bimodal. So I think either we get it by default using RLH++, or it actually requires a deeper understanding of what's going on inside of these models. I think the first advancement on this line is the development of understanding-based evals. Next are new approaches, right? Safer ways to design neural network programs. And maybe more ambitiously, it's the idea of full interp, where we actually reverse engineer the full thing the model's doing. I don't know if that's actually possible. Just like I don't know if P versus NP is actually possible. Now, these questions about developing better tools for reliability engineering, really, might be blocked on theoretical progress, scientific progress in understanding neural networks. So the question I'd like to explore for the rest of this talk is the question of what kinds of algorithms do neural networks learn? How do they learn these algorithms? In computer science, we have many different ways of talking about algorithmic structure. We have Turing machines, Boolean circuits, lambda calculus, finite state automata. All these different models of computation might be equally expressive, but they're not the same things. And so some are more amenable to addressing certain problems or talking about certain kinds of algorithmic structure than others. So which, if any of these, is the right foundation for talking about structure in neural networks? What are the right foundations for interpretability and alignment more broadly as a proper science? The perspective we're going to explore today is a perspective that's rooted in singular learning theory that examines the geometry of the loss landscape in relation to all these ideas. We'll look at two particular applications of SLT towards understanding generalization and understanding the development of algorithms inside of neural networks. At the very end, we'll close with what's next, a preview of what's up and coming in this field. So geometry. Let's start with the current day. How do we currently program algorithms in neural networks? Well, the structure we end up with in neural networks comes from a few basic ingredients. We specify an architecture, transformer, RNNs, Mambo, whatever. We compile lots and lots of data, right? We scrape the entire internet, at some point people's personal emails and chat histories, put it all in the cauldron, and we choose, I don't know, a ladle. Like we choose the optimizer, specify some hyperparameters, and we start mixing, okay? Now, when it comes to the question of where algorithmic structure in models comes from, I think a lot of these things aren't actually relevant. You need to choose the right hyperparameters for your optimizer, but I see it as more of a prerequisite than the thing that tells the model, how do you build an induction head? How do you construct an IOI circuit? Similarly, I think the architecture actually isn't that important. It's important in the sense that you need some minimum level of expressivity. You need a rich architecture, and making your architecture better reliably produces better models. But the actual specification of how models learn to transform information, that seems to be in the data. And that's the hypothesis we're going to go with, that structure, algorithmic structure, that ends up in the model is latent in the data. Now, we've seen evidence of this from many different perspectives. So it dates back to work done on vision models, right? Many different architectures, many different optimizers, in some cases even trained on slightly different data sets, converge to similar representations of the data. So here we see curve detectors, which appear to be very similar across different models. I'm thinking of examples like recent work by Techmark's group, where they show that repeating cyclical structure in the data, in this case, days of the week, months of the year, is reflected as cyclical structure inside of the model. There are some theoretical cases where we can do a full analytical treatment, and you can see clearly the relationship that structure in the data in the form of correlation matrices has to structure in the model. And again, I think back to these examples where we understand in some detail what's going on inside of transformers that are learning algorithms that we can then read out. And of course, in some cases, features in the model literally represent structures in the data, like the Golden Gate Bridge. So structure in the data leads to structure in the model, maybe. But how? How does data determine structure? Well, the perspective that we're going to be exploring is that data influences structure through geometry. We'll start with the second part of this, the relationship between geometry and structure. Look at a particular example of this relationship. That example is that of simpler models as having more volume associated to them. Let's look at an actually very concrete example. So we're going to take a problem where we're trying to learn a simple linear transformation. So the data is generated by some linear transformation t of inputs x into y. But our model is this weird thing that involves multiple matrices. In this case, just two, but potentially many matrix multiplications stacked together. You stack a bunch of matrix multiplications together, and you get another matrix multiplication. So it's equally expressive, but it's a little weird what's going on here. What you find is that if the true transformation is not full rank, then the associated solution is going to have more free parameters. So you can see here, for an example where we have a 2x2 transformation, that if that transformation is this 1 in the top left corner and zeros everywhere else, you can decompose it into this product of matrices where you have these two free parameters. And actually, you have additional free parameters that I haven't showed here. But the point stands that these two parameters span an entire plane in parameter space, where every point on that plane implements the same transformation. Okay, so low-rank solutions in this model class, in this weight space, occupy more volume than other solutions. Let's take a look at one more example. That's from dead neurons in a ReLU multilayer perceptron. So the ReLU is going to be a linear transformation of the ReLU function, which takes the max of 0 and some activations of A times B, A times X. Now I want you to consider what happens if the distribution of activations is such that activations A times X index I are always negative. Well, you run them through this transformation, and you get out a 0. Now, the thing is, you can multiply a 0 with any number, and you still get a 0. So what this leads to is a free parameter in the output matrix. You get an additional directional loss landscape that you can change your model without changing the thing you're implementing. So that's more volume associated to the solution. I can move this left or right. So there's an additional kind of degeneracy here where I can do some transformations in the A matrix without actually affecting this. So there's more volume associated to this solution. As soon as I cross over so that some of my activations are negative and some are positive, this breaks. And suddenly, the role that B has is not negligible. It actually changes what kind of output I get here. If we push it even further, then we get another situation where now my activations are always positive. So my transformation actually acts like this deep linear network that we saw earlier. And you get the same degeneracy, you get the same symmetries that you would get in that case. So again, if your transformation is low rank, then this is going to occupy more volume. So very clear examples, things that you would encounter in real everyday neural networks where a simpler model that uses fewer degrees of freedom occupies more volume in parameter space. Now, the idea of looking at volume in parameter space is an old one. It dates back to at least Schmid-Huber, like all good ideas in neural networks and machine learning. But the conventional treatment is erroneous in that it assumes that neural network landscapes look like the left-hand side here. It assumes that they look like a basin, something that's parabolic. When in fact, as we saw in these previous examples, you usually have degeneracies. So directions you can walk along that don't change the loss. As it turns out, the volume, the behavior of the volume, is dominated by the influence of this degeneracy. Degeneracy has a much larger effect on volume than broadness or curvature does, as measured by the Hessian. Okay, so you can't ignore degeneracy. You can't ignore this property if you want to understand volume. And this turns out to be the defining property of singular models, which gives singular learning theory its name. This has an important consequence, which is that different models in the same parameter space can occupy different volumes. Their local geometries look different. And that turns out to be important for how the learning process proceeds and the kinds of models that you end up with. It's also important because degeneracy breaks classical learning theory. What I mean here is that classical learning theory typically assumes that models are non-singular. So when you have a model like a neural network that is singular, all these classical results don't apply. In that sense, singular learning theory is really a relaxation of some overly prescriptive assumptions in the classical literature. That's why I've said that singular learning theory is more like a prerequisite to any mature theory of deep learning than an option in and of itself. You have to deal with the fact that models are singular, that they have these degeneracies. Okay, so simpler models occupy more volume. And that's quantified by what's called the local learning coefficient, lambda. The local learning coefficient measures the volume scaling rate. So suppose I have some toy landscape here. We've got two parameters, and the height indicates the loss. What I'm going to do is I'm going to ask for a given reference local minimum, how many solutions are almost as good as this point? So within some height epsilon, what is the area of parameter space that is less than or equal to that height? What you find out is that the volume here, in this case area, scales like some constant times epsilon to the power lambda, where lambda is the local learning coefficient. If you have a paraboloid, this exponent is maximized. It's equal to the number of dimensions divided by 2. So in this case, 2 divided by 2 equals 1. If you have something more interesting, like x to the 4th plus y to the 4th, then the learning coefficient can be smaller. In this case, you get a half. Or something more interesting, x to the 4th times y squared, you get an even smaller number. Okay, so what we see here is very clearly, these two bottom examples are degenerate. Their volume scales faster when you're close to the minimum than it does for the regular case. Now, lambda is, as it turns out, the natural way to think about model complexity for neural networks. As I just described, for non-singular models, for regular models, the learning coefficient is a fixed number. It's equal to the number of dimensions divided by 2. For so-called minimally singular models, the learning coefficient is precisely the effective dimensionality. Minimally singular models are models that look basically parabolic, except for a few directions along which you have an actual valley. You can move along this valley, and it doesn't change the loss at all. If you have more interesting examples, though, directions along which the loss doesn't look quadratic, but like some higher power, that's a form of degeneracy that is not captured by this minimally singular case. And so the learning coefficient is actually a richer notion of model complexity than just parameter count. There's more going on inside of it. From an information theory perspective, the learning coefficient measures the number of bits required to have the error. So this is actually related to how good the model is at learning. The learning coefficient is related to how many bits it can extract from the model can extract from data. What you notice is, over time, if the learning coefficient changes in a model, it might be an indication that it's actually getting better at learning. This is related to questions around meta-learning and how good is the model at extracting information from data. Now, theoretically, the learning coefficient is related to the real log canonical threshold of algebraic geometry. Right? This is where the math comes in. Now, unfortunately, this procedure is usually intractable for neural networks. Fortunately for you, that means that I don't have to go into the details of this procedure. That's because there's an empirical approach where we can estimate the learning coefficient from samples, from data. And that approach involves looking at the average local increase in loss. So we take some starting minimum, we measure the loss of that minimum W star, and we measure how much higher the loss is in its neighborhood than at that point. That's what this expression reads. So in this sense, the learning coefficient is related to fragility. It tells you how much does a typical perturbation harm the performance, increase the loss. And to actually perform this estimator, to use it, what we do is we use stochastic gradient Langevin dynamics to estimate this expectation value, which consists of basically training with SGD plus adding a little bit of Gaussian noise to make sure it's moving around. And we add this localizing term, which is like a weight decay term that makes sure that our samples are sampled close to our starting minimum. Okay, so it's possible to estimate the learning coefficient, and my collaborators have shown that it's possible to do so in some cases accurately and scalably up to hundreds of millions of parameters. And we started looking at this in larger models, maybe GPT-2, small scale. So this works. At this point, we think it's something that you can apply without much further effort to models on the order of 1 billion parameters, and probably all the way up to the state of the art. Okay, so simpler models mean more volume, particularly in terms of higher degeneracy as measured by the learning coefficient. Now, this relationship goes both ways. So I don't want to suggest that it's just simplicity that induces more volume, but really you should think of these as two sides of the same coin. So I want to illustrate that with an example from this toy model of superposition that Anthropic introduced. Particularly, I'll talk about work by my collaborators, follow-up work by my collaborators. So the model is a very simple autoencoder. What we do is we perform this transformation from RC to RR, linear transformation. Then we take the inverse, or we try to. We can't because it's a linear transformation. And then we apply this ReLU nonlinearity, and there's a bias involved. Okay, so in general, because this is compressing the inputs, it's not possible to do this with high fidelity. You're going to lose some information in the inputs. However, we're going to sample data from the high sparsity regime. So each sample is a one-hot vector that has a value in one index and zeros everywhere else. Now, what this means is for this specific data distribution, it's actually possible to achieve perfect performance. To achieve perfect performance, you have to use superposition. So what you find is we're going to take the case where we're mapping from 6 dimensions down to 2 dimensions and back up to 6 dimensions. Then you can represent the columns of this weight matrix as 2D vectors, and we're plotting them here. And you see that those 2D vectors span a regular polygon, a square, and a pentagon. So in general, the solutions for this model are precisely regular polygons. So what you can do is you can actually theoretically compute the loss of these different kinds of solutions, and you can estimate the learning coefficients associated to them. And what you find is this relationship between the loss and the learning coefficient, in which increasing structure, as you can visually read off of this weight matrix, is linked to an increase in the local learning coefficient. As you go from 4 gons to 5 gons to 6 gons, as you start using more biases, the learning coefficient increases. The structure becomes more fragile. There's less volume associated to those solutions. So 2 sides of the same coin. If a model is simpler, it will have more volume associated to it. Models that have more volume associated to them are simpler relative to your data set. This is important for another reason, principally because having more volume means the solution's easier to find. And that's quantified in the Bayesian setting by singular learning theory's free energy formula. So it turns out for the Bayesian setting, you can recast the problem of learning as a variational problem, as an optimization problem, in terms of minimizing this free energy. Okay, minimizing this free energy requires a trade-off between this loss term, L sub n, and the complexity, the learning coefficient. It's a trade-off that depends on the number of samples n. So as you sample more and more data, you're going to end up preferring the linear term in n, the loss term, over this logarithmic term, because the linear term scales faster than the logarithmic term. So you'll come to prefer higher accuracy, lower loss solutions, even if they're more complex. What we get is a data-dependent form of Occam's razor that's satisfied automatically and implicitly for Bayesian learning machines. Simpler models have more volume, are more degenerate, and this is linked to implicit regularization. So it's easier to find these solutions, and you end up finding them more often. Okay, so what does this say about generalization? Well, Occam's razor tells us about generalization, right? You should prefer the simpler model, all other things being equal. So the simpler the model is, the better you generalize. And this is measured by the Bayes and Gibbs generalization errors, again, in the Bayesian setting. So the Bayes generalization error, B sub n, is given by this KLI divergence between the true distribution, Q of x, which is the process that's actually generating the data in our data set, and our predictive distribution, the probability of a sample given a data set. This predictive distribution is given by this formula. So what we're going to do is we're going to take our posterior here. We're going to make a prediction with each individual model. Every choice of weight specifies a single model. We're going to predict the probability according to that model. And then we're going to weight that model's prediction by the posterior, by how likely we think that model is after we've seen the data. And we integrate over all of parameter space. Now, the leading order term for the Bayes generalization error is given by the learning coefficient divided by n. So models that are simpler, that are more degenerate, generalize better. And if you sample more and more data, you'll generalize better. For classical models, again, the learning coefficient is a fixed number. It's equal to the number of dimensions divided by 2. So classical learning theory predicts that neural networks should overfit because it's looking at the wrong measure of model complexity. You should not look at the explicit parameter count, but you should look at the learning coefficient. Coming back to this full relationship between data, geometry, and structure, how does this relate? Right, we've been sort of working our way backwards. And the arrows so far have been in the reverse direction. Consider what happens when I change the data distribution. The geometry of a loss landscape is a function of architecture and data. So what this will do is it'll lead to a change in geometry. What we expect is that this should be associated to a change in structure. Maybe more appropriately, I should say, a change in the mode of computation of the model. If you detect that a change in the data distribution leads to a change in geometry, it's a sign that the model is going to compute differently on those inputs. This is why we see a path using SLT to build up a rigorous understanding of out-of-distribution generalization. By looking at how changes in data change the geometry and understanding the relationship between geometry and structure. This is what we call structural generalization. To give you an inkling of what this might look like, consider that the learning coefficient can be easily modified to give you a richer signal. So one thing you can do is, the learning coefficient, this estimation procedure, depends on sampling data from some distribution. You can swap out the distribution you use to estimate the learning coefficient. So you get this data-restricted learning coefficient that tells you about complexity with respect to different kinds of data. Another thing you can do is you can restrict the weights. So I can freeze a bunch of weights and let my gradient updates take place in only a subset of the weights. Maybe it's a particular layer, maybe it's a particular head, maybe it's some circuit. And I can measure the amount of structure in that part of the model. So together, the learning coefficient gives you a way to probe data-dependent structure in parts of the model. Bringing this back to alignment, right? Currently, what alignment looks like is it looks like engineering the data. RLHF, RLAIF, constitutional AI, all these look like modifying the training distribution and continuing training. The question I'd like to ask is, do these techniques successfully reprogram the model? Do they actually meaningfully change geometry? Or do they only scratch the surface? I mean, I don't think there's a better picture to describe the situation than this one. This is it. So coming back to structural generalization, the real question we'd like to answer is, what structure survives a distribution shift? What breaks? So here's a very toy illustration. Suppose I have some free energy landscape. I've got these two minima. Currently, we're in this minimum, the harmless, helpful, honest minimum. But then, oh no, a distribution shift. What happens? Which pattern survives? Is it the harmless, helpful, honest pattern? Or is it a pattern that's deeper in the data? Pattern like power seeking, goal-directedness. The things that we worry about when we talk about instrumental convergence. This concern that capabilities might generalize further has been called the sharp left turn by Nate Suarez. I think it's actually pointing to a deep problem in learning theory, something that we can understand better and that we should try to understand better. So SLT opens up a path to building out a science of out-of-distribution generalization by looking at changes in geometry related to changes in geometry, and data related to changes in geometry. And we believe this is on the critical path to addressing certain core problems in alignment, like the sharp left turn. All right, I haven't said anything about developmental interpretability yet, right? So what about development? Well, let me come back to the question of how does geometry determine structure? And the answer is that geometry determines structure through the learning process. If you have SGD, the basic idea in dynamical systems theory is that it's the structure of critical points, of singularities, in some potential landscape that determine qualitatively where you end up. So the idea that singularities, these critical points and the degeneracy around them, influence learning dynamics is unsurprising. On the other side, in the case of Bayesian learning, SLT tells us exactly what the relationship is. And it tells us how singularities influence the Bayesian learning process. Now, SLT is currently a theory of Bayesian learning. It's an open problem of extending the Bayesian theory to SGD. We think it can be done, but I'm going to skip over it for now and focus on this Bayesian case, because I think the intuitions that we take from it will mostly transfer readily to the SGD case. Okay, so what is the Bayesian learning process? The Bayesian learning process is the question of what happens to the posterior as you sample more data. And so we go from n samples to n plus 1 samples to n plus 2 to n plus 3. In the regular case, again, your model is defined by the minimum of this free energy as a function of the number of samples, the loss, and this fixed number. What you find is that the posterior just converges slowly to the optimal values. So you'll get this slow, boring convergence to something that looks more and more Gaussian, more and more peaked. For singular models, this trade-off can change suddenly, sometimes. So what you notice is that for given n, the posterior can jump occasionally from one kind of critical point to a different kind of critical point. That change in geometry is an indication that there's also a change in the underlying mode of computation taking place in the model. So what does that look like? Consider two different regions of weight space, W1 and W2. W1 is less accurate. The loss is higher, but it's simpler. The learning coefficient is lower. If I plot the free energy associated to these different regions as a function of the number of samples, I get this picture. The overall free energy is going to be, of the entire model class, is going to be determined by the minimum across these two different regions. So what you find is that as you increase the number of samples, there's a critical value of n at which the minimum of the free energy jumps from W1 to W2. And so you get this Bayesian phase transition. This is unique to singular models, because for regular models, this learning coefficient is a fixed number. So what we see is that singular models perform this internal version of model selection. In the regular case, you have to explicitly set up a bunch of different architectures that you'd like to compare and contrast. For the singular case, the model's already automatically doing a kind of internal search between different kinds of architectures, different kinds of algorithmic solutions, for the best trade-off is for the problem at hand. So if you make your model class big enough, you've got a lot of choice to select between. In the case of toy models, like the deep linear network we saw earlier, like these toy models of superposition, learning is actually a succession of critical points. So you see that the loss comes down in this stepwise fashion, and the learning coefficient in green goes up in this opposite stepwise fashion. For the toy model of superposition, the loss starts up, the model transitions from one kind of foregone to a different kind of foregone, comes down, the learning coefficient jumps up. It settles there, it's stable in this state, and then there's another transition in which it jumps suddenly to a five-gone, where it stabilizes. So you can characterize these phase transitions and analyze them with SLT. In the case of the toy model of superposition, you can actually see that the set of allowed transitions is predicted by SLT. So knowing just the loss and the learning coefficient, you can predict which kind of model can jump to which other kind of model. And you predict that, and all of the observed transitions are allowed in this way. Another example that I'd like people to look at more is grokking. So grokking, at this point, I think is pretty clearly a transition in the same Bayesian sense that you see here. It's a transition in which the learning coefficient comes down later in training than training loss. This is work by Nina Paniksari and Dmitry Weintraub. This is ongoing work by Wilson Wu. So I think there's stuff to do in grokking. I just threw this up here because it was on the screen yesterday. I think at this point, a fair criticism is, yeah, but these are very toy models. Right? These are very small models on the order of a dozen parameters, maybe a few hundred. What about larger models? So with larger models, you observe that the loss decreases pretty smoothly. So there doesn't appear to be this stepwise learning going on. However, sometimes you'll find this hidden stage-wise development. So if you plot the learning coefficient over training time, you'll see that it reaches these plateaus where it stabilizes before continuing on its journey. Upon further inspection, you find that these plateaus are meaningful. They separate stages in which the model is first learning bigrams, then it's learning n-grams. It starts forming the induction circuit, it finishes forming the induction circuit, and it stabilizes. So using these geometric indicators, you can, in an unsupervised way, detect these meaningful stages. So development seems to be macroscopically simple and organized into interpretable stages. These stages, I could call them transitions. They're not necessarily sudden. And so this is the case as well in biological systems. You get these cell differentiation events that are well modeled as transitions. But in terms of wall time, in terms of the number of training steps, they're not necessarily sudden. So that's why we've jumped to, we've transitioned to using more the language of stages. Because transition can give a sort of misleading idea that something has to happen instantaneously. Okay, so why def interp? Well, I can introduce developmental interpretability completely in terms of completely on its own terms. Right? Sometimes it's easier to understand changes rather than it is to understand the final output. The same idea motivates a lot of work in developmental biology, for example. The obvious follow-up question is, which changes? What's the right unit of change? If it's the case that you have to analyze every individual training step, well, then developmental interpretability isn't going to help you much. Right? The problem is still intractable. If it's the case that learning is divided into stages, and there are maybe lots of stages and overlapping stages in different parts of the model, but still finitely many stages and fewer than there are training steps, then maybe this provides a very meaningful axis of reduction. So SLT provides a path to a more rigorous and scalable science of interpretability. Science of interpretability that starts by interpreting the developmental process. And we think in some way that a future version of SLT might be the natural way to talk about computation. That a geometric approach might be the way nature intended us to think about computation in neural networks. Okay, so what's next? Let me jump back first to where we were a year ago. So a year ago, we'd organized this conference to bring together SLT people and alignment people and think a little bit about the potential applications of SLT to alignment. What came out of that was developmental interpretability. It's this agenda to understand how structure forms. Now, since then, we learned, first of all, that SLT can inform new measuring devices. This is the principal prerequisite to theory being useful, is that it can inform devices that you use to actually go out and measure things in practice. So you can start this theory experiment feedback loop that is the sign of a mature science. We found that in simple models, phase transitions are real. It's not just an abstract prediction of SLT, but they actually exist in these systems. In some cases, SLT can actually predict the allowed transitions, and our measuring devices can detect them. In larger models, hidden stage-wise development seems to be common. In many cases, interpretable. It's a sign that a developmental approach is viable and a fruitful way to explore the development of structure, or to explore the structure you end up with in neural networks. Coming soon are 2 new papers. So in the first, we introduced these restricted local learning coefficients. We showed that they can be used to reason about the differentiation and specialization of different attention heads in small language transformers. This reveals, well, I'm not going to, I'll give a little hint. So this reveals potentially new minimal circuit, something that's more foundational than even the induction circuit in neural networks. In another paper we're finishing up, we show that SLT explains algorithm choice in transformers trained on linear regression. So if you're interested in this, ask me about it afterwards. Now, over the next half year, we're pursuing projects in 2 main pillars. Right? So there's foundational work, scientific work on understanding and advancing developmental interpretability and structural generalization. And then there's work we're doing in terms of trying to apply what we already have as quickly as possible to making progress on alignment. So foundational work first. We'll explore the development of GPT-2 small. And so scaling this up further, showing that these techniques continue to reveal interesting new things about what's going on in language models. DevInterp 2.0 is about going beyond the learning coefficient. The learning coefficient is just a scalar, right? Now, the fact that it depends on data, depends on training time, it depends on your restriction of weights, means it's actually a lot more than a scalar, and there's a lot more information contained in it. But still, eventually, we would like to have richer signals, better metrics. So there are ideas in terms of certain weight and data correlation matrices for going beyond the learning coefficient. And we'll see the foundations of structural generalization start to be established that reveal this link between data and structure. On the applied side, like I said, we're trying to move as quickly as possible to making real-world progress on alignment. And we're starting with a project that examines how reversible safety fine-tuning is. Now, if you remember, I said that the learning coefficient is related to how easily the model extracts information from data. We think that this can be used to say something meaningful about how reversible safety fine-tuning is on given models. We also think the learning coefficient can say something about how vulnerable models are to jailbreaking. For example, many-shot jailbreaking. And that it can be used to reason about the presence of backdoors or deception in, for example, these sleeper agent models. Eventually, we hope that this line of approach will lead to the first understanding-based evals, which we think are possible in less than a year. Now, before I close off, I would like to turn this around on all of you and share some questions I'd like somebody in the audience here to answer. Sort of inspired by Vikrant's talk yesterday. What can SLT say about deep double descent? I think it'll basically be solved applying this, and it's not a very hard project that you you can do. Now, there's more work to be done on relating SLT to grokking, and I'm particularly interested in how does this story in the learning coefficient and these SLT-derived metrics, how do they relate to circuit efficiency? Does a low learning coefficient imply low intrinsic dimensionality of the gradients? Seems like a natural hypothesis that if you have many more redundant directions in parameter space, that the intrinsic dimensionality of your gradients will be lower. And I mean, the lottery ticket hypothesis is obviously wrong, right? Can somebody put that to bed? We actually have a list of a lot of open standing problems that are a good place to start if you're interested in doing an introductory project on something in developmental interpretability or adjacent to it. Okay, so I'd like to thank the team. We've been growing recently. None of this would be possible without the people here, nor without our many awesome collaborators at the University of Melbourne and beyond, so the Gradient Institute. To come back to this picture, right? Oh. Alignment might be difficult, okay? But on some questions, some core questions of alignment, we see the hints of a possible solution. Through structural generalization, we see the first steps we might take to understanding out-of-distribution generalization more rigorously. Through developmental interpretability, we see possible new ways to develop scalable and rigorous tools for probing structure instead of neural networks. We can see a path forward. Thank you very much. Let's take some questions. Let me say one more thing. So we are hiring. There's an announcement on Less Wrong. There's a link right here. And I encourage you to check it out. Yes, Jan.
Yes, thanks for a great talk. We have actually 20 minutes for questions
Okay.
now, and also just will be running a tutorial. So if you want to, maybe you can introduce it briefly. If you got motivated to work on this, which is an excellent possibility, maybe you may want to join the tutorial. Maybe you can say a few words about what it look like.
Yeah, so the tutorial will look like what you make of it. If you are more interested in the empirical side, you can come and work through some of the demo notebooks we have. You can start looking at maybe some of these projects that we've put up. If you're more interested in the theoretical side, then I have a list of pen and paper problems that you can work through that I've asked my colleague Zach to compile. So, pick your poison. Yeah.
Yes, so as I said, you have 20 minutes for questions. I would actually start with a question. So there's this Tigma's group paper on the pizza and clock algorithm, which is also showing phase transition. You are in some sense proposing as the main thing, the learning coefficient is basically a complexity metric of the models. How would the metric incorporate the thing-based study, where we actually just fine-tune some parameter of attention in a transformer?
Oh, so there was a question about the pizza and clock, and then
yes. So there's this pizza and clock paper which I recommend everyone to read. You can post it on there are two algorithms how to do modular arithmetics, and they show in the paper that depending on hyperparameter changes of the network, the network learns either this algorithm or this algorithm, and it depends on the hyperparameter, and it kind of they show some basins of attraction where the learning process falls into one of the basins. But there is no change in the data, so the learning structure very clearly depends on the network. So how would single learning theory capture that?
Yeah, that's a good question. So if I remember right, part of this involves tweaking the weight norm. So if you have the free energy, Sorry, I just want to draw on the chalkboard. I didn't subject you to the full glory that is the free energy formula because there's a lot of pieces to it. But okay, so there are a few extra pieces here. The important thing is you have this constant contribution here, or this sub-constant contribution, and that's where you see the effect of the prior show up, but also the effect of explicit forms of regularization like weight decay. So if you look at the learning coefficient, the loss, the weight decay, some of these additional components, you might be able to actually model that correctly and see why the trade-off is the way it is. But this could also be a case in which the differences between SGD and Bayes actually matter. So I'm not sure.
Yeah, so I'm also going to ask a question. A related question to that. So I understand in Bayesian setting, once there is a phase transition between where the minimum is, the Bayesian learning switches the mode immediately. But if you look at the nucleation physics or something like that, the transition rate between the two minima can actually be non-trivial, especially if the boundary between them is high.
Mm-hmm.
And I actually have both heard intuitions for this energy boundary between the two being actually very high, and some intuitions for this actually being almost none.
Yeah.
So does SLT say anything about that? Because what is the relationship between the actual process and the Bayesian data?
So suppose we have this loss landscape. It looks like this. And we're going to draw. So let me tackle the first part of the question first. The Bayesian phase transition also has some characteristic time associated to it. So yeah, what you'll notice is if you plot this free energy as a function of time, and you have these two different solutions, there's some speed associated to how quickly they diverge. So even in the Bayesian setting, there's some speed, and the transition isn't necessarily immediate. You notice that the overall minimum of the system changes discretely. So in that sense, it's discontinuous, but there isn't a time associated to it. For the SGD case, there's this huge literature within thermodynamics looking at transition rates that I think could be brought to bear on this question, and I'd be interested to see it. I don't think anybody has tried relating, for example, the transition rate to the difference in loss between these two regions and other differences between them. Actually, no, there is one thing. So Guillaume Corluer looked at some of these differences between Bayes and SGD in simple examples like this toy one-dimensional landscape. And so there it seems to be the case that SGD is actually somehow stickier than the Bayesian setting is, where even as you continue to sample more data, at some point you get stuck in these degenerate local minima. But I'm not sure how that extends to larger models.
I'll follow up on it later because I'll be curious if SLT can say something about the size of the barrier. But that's a different question. I'll just pass on. Mike.
Hello, my background's in numerical thermodynamics, which is where I'm coming from, and I know some methods that might be interesting to you. We should talk afterwards. My question is the free energy formula. Can you explain it in a bit more detail and maybe explain where it's coming from or how it's motivated?
Yeah, yeah, I can. It comes back to this picture. You can find it.
There it is.
Wait, no, this one. This one, okay. So I think there are two basic things you should understand from this picture. So one is the role of integral transforms in analysis. So a very common trick that mathematicians use is you've got a a problem description in one representation, and you perform a transformation of that representation to get a slightly different transformation that maybe is more amenable to analysis. If this transformation is invertible, then you can apply the transformation, you can solve the problem, and then you can convert it back to the original initial representation. You have your solution. So that's what we see here going on with these arrows. So the thing we care about is either the partition function or the free energy. That's what we want to know. And you have these mappings you can use, two-sided Laplace transform and a Mellin transform, to get this zeta function. It's a different representation that has the same information in it. When you get to this point, you pull in the other main technique of analysis, which is you use complex analysis. And so you extend this analytically to the complex plane. And you can study the poles of this thing. And those poles contain the information you want. And then in order to actually read out the information from this new representation, you need what's called the resolution of singularities, which is the seminal result in algebraic geometry, which is a procedure for transforming that representation into something that is, again, easier to use. All of these transformations are invertible, so you get something that's easy to solve. You can just read off the learning coefficient, and you transform it back, and you have the original free energy formula.
So it's basically all the terms are from this transformation retransformation.
Mm-hmm. Yep. Yep.
So first of all, thank you very much for this nice talk. If I understood you correctly, the basic task is first to classify the singularities in order to have an understanding where phase transition can occur.
It classifies.
To understand where they are, what kind of properties.
Yes. Yeah, so here's a very simple example. Suppose you have two different models. Those two models have the same loss, and you'd like to know, are they doing the same thing? The natural next thing you should measure is the learning coefficient, and look at if the learning coefficients are different. If the learning coefficients are the same, it's a sign that these models are closer together in some way. If they're very different, then it's a sign that the models are doing something qualitatively different. So it's a high-level observable you can use to contrast, to compare different models. I'm going to give, again, this is a heuristic explanation that is slightly wrong, but, right? So you've got loss, that's the up-down direction, and then you've got sort of broadness in the sided-side thing. Again, broadness is not a word I would actually recommend using, but these are the first things you measure, and then there's richer information that you can start looking at past this.
So this is like coming from the observational point of view. But I mean, I could also imagine coming from the other side, from the more principle-based version, where, I mean, in physics, for example, singularities are always related to symmetries. And you were pointing out all these kind of symmetries earlier. And I was wondering if there's some sort of analogy that I can study the symmetries of the network and have some idea of the singularity structure.
Yes. Yes, I think so. Yeah, that's the same observation is true here.
So,
no, I can actually say a little more. So there was work that's coming out by a colleague of ours, Simon Lehelleur-Papin. He has a new derivation of the free energy, or not the free energy formula, but of the learning coefficient that takes a different route through all of this, through what's called jet schemes. So jet schemes are just the fancy algebraic geometer's way of talking about truncated Taylor series. So you take a Taylor series up to some order and you cut it off. That's a jet scheme. And so there's a new derivation in terms of the free energy of the local learning coefficient in terms of those jet schemes. And that, I think, is more closely related to a perspective in terms of local symmetry. So that might be the place that you're looking for. Scheme.
Hey, earlier on you showed that there's two different ways how you can get the generalities in the HAAISS. One is right?
Yeah.
You know, are you sure that those, like, do you think both of those are relevant in practice?
That's a good question. So we know that the values are relevant. It's very easy to concoct many examples, and you can also just observe this.
I was asking about that one.
The other one's harder. So the question is like, does this thing actually happen? Okay, so Daniel Murfitt put out this post called "Short versus Simple," and it explores one possible origin for this kind of degeneracy. So I'll write it here. And that comes from another area of applications of SLT that we call geometry of program synthesis. So there the idea is you can take a Turing machine. A Turing machine, you know what the program is. You find some smooth relaxation of that Turing machine, so it's got a parameter space all of a sudden, and then you can apply SLT to that new parameter space because the model ends up being singular. Once you've done that, you can ask the question of what happens when this model is error correcting? If there's, for example, I misread a bit. I accidentally read or write a 1 instead of a 0. What Dan shows in that post is that if that's the case, that you are error correcting to more and more bits, it'll be associated with an increase in degeneracy of the second type. Now, this is in the case of Turing machines, so it remains to be seen that something similar could apply to neural networks. I think in principle, probably. But it is difficult to actually probe this, although I'm sure somebody has ideas.
I'm going to ask a quick follow-up because I'm a bit confused how it works when you apply SLT to neural networks with values, which are always locally linear. So in this case, you would expect there to be no quadratic functions. I mean, they could be quadratic on some, or they can look quadratic on some bigger neighborhood, but like there will always be an epsilon neighborhood where they're just linear. So they're the second kind of degeneracy cannot happen.
So
is that the correct reasoning? Is that relevant?
yeah, so okay, so one of the reasons we like deep linear networks is because we have the theoretical result for what the learning coefficient is for deep linear networks. And that's thanks to a result by Miki Aoyagi, one of the original SLTers. And I know that she's currently working on studying ReLU networks, fully connected ReLU networks. So I think she anticipates that it's possible to borrow this knowledge that it is locally linear to do something, to do some meaningful simplification there. But I don't know.
Yeah, I hope my question makes sense. I was wondering how sensitive is SLT as a theory of impact for linemen? So the underlying structures and the hypothesis for computation. I'm thinking about like dense versus sparse and like correlational versus like clearly defined circuits.
Oh yeah. I think this is somewhat an open empirical question. It remains to be seen. But I will say that this local learning coefficient, right, where you have, let's see. I've drawn this many, many times by now. Like, what I'm going to do, I've got the loss landscape. I'm going to draw the set of minima at the bottom. So when I do SLT, when I do SGD to sample things, I'm going to like jiggle around like this. Okay. Let's see. So this is, in a sense, a kind of ablation already. If I were to restrict this to take place in only a specific attention head, then I'm in some sense already performing a kind of ablation analysis, where I like knock out weights and see how they respond. And so that's a causal understanding that you're able to get from that if you do it right, I think, in principle. Yeah. So in some sense you can see this as, well, at least what we're currently doing is complementary to mech-interp, which is mostly focused at the level of activations. We're currently thinking more of structure in weights. Okay, can you elaborate the semantic difference between?
I'm looking at it from an attention point of view. So in attention, our logic is that we get some dependency based on the whole sequence.
Mm-hmm.
So I want you to understand that in an unsupervised scenario, can we see some relevance in the sequence as well?
Yeah. I'm not sure. Okay, okay, just to be clear about this. So the way we looked at these, the way we identified these different stages is by looking at additional metrics. So behavioral metrics and additional structural metrics, where we're looking at, for example, what different parts of the model are doing. If you ablate some part of it, how does it respond? So the full analysis requires currently a combination of these techniques. And the unsupervised part is just in detecting the boundaries between stages. I think eventually there will be richer techniques that can already suggest sort of what parts of the model are doing, but that's down the line. That's like DevInterp 3.0, 4.0, one thing at a time.
Thank you.
Thanks for the talk. Apologies if you answered this question already, but what's the definition of the local learning coefficient when you're not next to a local minimum?
Yeah, that's good.
As it happens in like
Yeah.
post-it training?
Good. Yeah, I swept this under the rug, right? Okay, so theoretically, there currently is no definition. It's a weird, nonsensible thing to do. Empirically, it seems to be fine. So we don't seem to be running into problems with this. We get results that seem meaningful. Yeah, I think maybe I'm going to sketch sort of an intuition, and you shouldn't read into this too much. But suppose I am, pull out another color. Suppose I'm like right here. This is my local minimum. If I start moving around, I'll be influenced by this direction. And so maybe what I actually end up sampling is the effects of the nearby singularity, even though I don't start at that position. And this will introduce some error because the minimum I'm measuring with respect to isn't the actual minimum I should be measuring the loss of. But at least if you do this iteratively, the errors will be somehow the same locally. You might still get meaningful signal by looking at the critical points of this graph.
Sorry, I'm still a little confused. Is this like, are you saying you find the local learning coefficient for the closest minima and that's the number you're using, or something else?
Empirically, what we do currently
Yeah.
is we just measure the loss at that point, of the starting point, even though it's not a local minimum. What you can do, and some people have done in certain settings because it helps, is you can train for a few steps first and see if you reach a local minimum then, and then measure the loss. And so this training procedure is going to have to involve making sure that you're sampling close by, but then you definitely find some sort of local minimum.
Thank you.
I only have one more question, but I'm not sure how open-ended it is.
Done?
Yeah, sure. Actually, let's go with your question first.
Mhm.
So the question I have is like, my understanding is that this attempt to understand generalization
Mhm.
in deep learning is something that there's been theory people from CS and math doing for 5 or 10 years or something, and they've seen limited success in understanding generalization from the theoretical perspective and so on. Like, what's that community's reaction to what SLT is doing? Are they like,
I just don't think they've engaged with it much. I don't think they're aware yet. So maybe this is on us, and we need to do a better job of communicating to them. But I think it's mostly just a lack of awareness.
what would be your anticipated reaction? Like, oh man, we missed this like important correction to what we were trying to do or something.
Yeah, that's exactly what I expect. So I expect that in like 2 years, 3 years, there will be widespread interest in this kind of thing. And this might be like basically yeah, that's what I expect.
And maybe one follow-up question is like, what do you think is the most compelling thing to show to someone who's been doing deep learning theory? Like, here's like the result that demonstrates to you that what we're doing is like really good.
That's a good question. So I think there's a new version coming out of the quantifying degeneracy paper, which looks at the role that different choices of optimizer parameters and like details like batch size have on the learning coefficient. And you see that many of these interactions and dependencies that people have in the past empirically linked to implicit regularization and the model generalizing better sort of seem to be collectively explained by the local learning coefficient being lower. So I think this is the kind of unification that might go ways to showing them something, but I'm not sure. So I should think more about exactly what the generalization community would like to see. Because I think there is some stuff that they do that's very interesting. So specifically coming from a more information theoretic bent, there are a lot of very interesting things that people have done with generalization bounds, but they typically involve quantities that you can't estimate, that you just cannot tractably compute. So I think that's the main limitation there. And that some of this work that's linking this perspective to an information theoretic perspective and the minimum description length principle might close the bridge between the communities.